Welcome friends to optimal control course. So, we are starting this course from this lecture and the complete course will have the 40 lectures in this. Optimal control is basically optimization approach has been used to develop the control, and how we develop this optimal control for a given system, that we will study in this course. How we use the optimization process to get the control, that we will study in this course. So, in today's lecture we will discuss what actually optimal control is and how we can formulate a optimal control problem. As we know, this optimal control is basically based on the optimization technique, and different optimization technique we will study in this course. The content of this course are taken from these 4 references. All 4 are the books. The first one is the D.S. Naidu Optimal Control System, published by the CRC Press. Our second reference is the D. Kirk Optimal Control Theory and Introduction, which is published by the Prentice Hall. Third reference is M. Gopal Modern Control System Theory, which is published by the New Age International, and the last book is the F. L. Lewis Optimal Control. So, reference 1 to 4 are normally contain all the content of optimal control theory. The third reference, M. Gopal book, has discussed the complete modern control systems, in which in detail the study space the state space analysis has been analyzed, and how this state space analysis is applied to the optimal control, that all is discussed in modern control system by M. Gopal books. As we said, our optimal control is basically based on the optimization. Now, question here is what actually the optimization is. Optimization means we have to determine the optimal value of a cost function, means the system variables we have to determine which is giving me the minimum cost, minimum of, say, the in our control, if we will talk about this, may be the giving me the minimum error in my required output and input, where input is my desired input, output is the actual output, the difference is the error, and we are trying to minimize this error. And once we are minimizing this error, what will be my states and what will be my control. So, if we want the optimal control which will minimize my error, so error we can represent as my performance index. So, this means optimization means to determine the system variables if my performance index, or we can say the cost function, is minimum. In general, optimization techniques depends upon what the approach we are taking. My approach may be algebraic or geometric. What is my interest? It is a single or multiple. Interest means, as we said, our objective is to minimize my cost. The cost may be my interest. It may be I want to minimize the error in my system. So, error will be my interest. It may be I want to minimize the fuel consumption in a system, in an automobile or in any vehicle. So, in that case, that will be my interest. So, what I want to minimize, that is my interest, and interest may be the single interest or the multiple interest. Sometimes we want to minimize the multiple things. So, that we call the multiple interest. As we are dealing with the control, so means we have to take the signals. So, my third point on which optimization is depends, that is what is the nature of my signal. That may be deterministic or stochastic, means I can have the signals in a pure form or I can have the signals affected by the noise, which we call the stochastic signal. And the stage may be single or multiple. Stage means whether in one shot we are getting the optimal values or we are using the multiple stage to get the optimal value. Optimization we can see in the two forms. One we call the static optimization and other we call the dynamic optimization. Static optimization means, if we will talk in terms of the control, means I want to control the plant under steady state conditions. So, I am not considering the transients in the system. For example, suppose we want to control a DC machine which is operating at a given speed. So, if I will take the DC machine model, it may be dynamic in nature or it may be static in nature. Static in the sense we are writing the equation by which we are describing the machine simply by the algebraic equation, like V equal to E plus IR. So, in that case, if my speed change from say one level of the speed, say 1000 rpm to 1200 rpm, then at steady state what are the parameters? Another example which we normally use in our power system as electrical engineer, if we will see, then we want to allocate the power generation of the different generating units. So, in that case we will optimize the system to minimize the cost of our generation. So, to meet out the demand in the system, what should be the generation of the different generators, so the cost of generation remain minimum. So, this optimization approach is called the static optimization. From control point of view, we can say controlling a plant under steady state condition, my system variables are not changing with respect to time and the plant is simply described by the algebraic equations. So, such a optimization problem can be solved using the ordinary calculus. If we have the constraint optimization, then we can use the Lagrangian multiplier approach and the complete formulation may be linear or non-linear. So, the linear or the non-linear programming approach can be adopted to solve such a optimization problem. In control, normally we deal with the dynamical system. Dynamical system means if we are changing any of the input may be the disturbance input or may be the set point. If this is changing, then how my output is following to these signals, that we have to normally study, and we describe our system in terms of our differential equations, and the solution of the differential equations means the system variables we normally observe with respect to time. Like we have taken the example of a DC motor, we can take, if we are changing the speed of a motor, let us say the set point we change from 1000 rpm to 1200 rpm. So, how the speed is reaching to 1200 rpm, that is important, and that period we normally call the transient period. So, this transient analysis normally is required in case of our control system, and once we will such a system we will apply the optimization technique, then that optimization is normally called the dynamic optimization. In dynamic optimization, we control the plant under the dynamic conditions, whether my system is suffered by the disturbance at a given set point. So, my system has to return to the same set point, and during this change how dynamically my system is behaving, that is our study. So, we are controlling the plant under dynamical condition, system variables are changing with respect to time as we discussed, and the plant is described by the differential equations. If we have the continuous time system, we have the differential equations, and if we have the discrete system, then we have the difference equations. So, that is our dynamic optimization, and the solution technique for the dynamic optimization are the search technique. Nowadays the heuristic approaches are very popular to determine the optimal values of a dynamical system. This heuristic approach, something like your genetic algorithms, PSOs, and a many number of the heuristic approach are available in the literature, we can use to find the dynamic optimization. Another approach, which are our classical approaches, that are the variational calculus, or we also call the calculus of variation, dynamic programming, Pointryagin minimum principle, which normally we used. And the objective of this course is to study particularly these three approaches, which is variational calculus, dynamical programming, and the Pointryagin principle. So, in this course particularly we are concentrating on the dynamic optimization problem and how a dynamic optimization problem can be solved using the variational calculus or calculus of variation, or using the dynamic programming, and if my system is constrained system, then how we can use the Pointryagin minimum principle to solve a optimal control problem. So, dynamic optimization techniques in this course we are using to find out the solution of a optimal control problem. What is the optimal control? The main objective of the optimal control is to determine the control signals that will cause a process to satisfy some physical constraint and at the same time extremize a chosen performance criteria, which we also call as a performance index or cost function. So, how we are setting our objective? Main objective is we have to determine the control signals, means what the input going into the plant, that should be controlled input, and how we are controlling this input, that is our main objective. We normally obtain this optimal control signal in such a way that it will satisfy the physical constraint, which is nothing but my plant, and at the same time extremizing means either minimizing or maximizing a performance criteria, like we have discussed about the minimization of the error, means we select the control in such a way that my error should minimize, and optimally how we will get this, that we will study in this course. So, that is my optimal control. How to solve this problem, that all we will study in this course. So, the first step to a optimal control problem is, first of all we have to formulate a problem. How to formulate a problem, that we will see, but in formulation of the optimal control problem, first of all we must know the mathematical model or the mathematical description of the process which we want to control, and this normally this modeling we will have in a state space form. As we already know, any physical system can be modeled if it is single input single output. So, we can also model it in the transfer function form, and in case of the multi input multi output we normally model in the state space form. Single input single output system can also be modeled in state space form. So, in this course particularly our prerequisite was the student must have the knowledge of the classical control as well as the modern control. In modern control normally we will use the state space modeling of a system. So, in general my system modeling is in two forms. The first one is the transfer function and second is in the state space. Transfer function model is normally of single input single output with initial conditions all initial condition is 0. So, with this we can model a system in transfer function. State space may be single input single output or multiple input multiple output, and initial condition can exist. So, state space representation is more general in nature. So, therefore, we utilize state space modeling to represent a system or to formulate a problem for optimal control. So, what is the state space model of a system? That normally we represent the system as x dot t as at xt plus bt ut and yt as ctxt plus d of t ut, where x is a vector of n cross 1, u is also a vector, let us say m cross 1, and y is also a vector, let us say p cross 1. So, if we have a n order system having the m number of the inputs and p number of the outputs, we can write x dot equal to ax plus bu and y equal to cx plus du. So, if this is the case, so this is n cross 1 and this is m cross 1. So, my A vector will be A is a matrix of size n cross n and B will be a matrix of size n cross m. Y is a vector of P cross 1 and X is N cross 1 and U is M cross 1. So, naturally C will be a matrix of P cross M and D will be a matrix of P cross M. So, this is the mathematical model in state space in which we can represent any physical system, whether a single input single output or multiple input multiple output, or whether my system initial conditions are 0 or there exists the initial condition. So, this is the general description of a plant in state space which we have to consider. Block diagram form of this system is, we can have this is x dot. So, this will be x, this is my matrix A, x dot equal to Ax plus B. So, this will be my U and U is this may be my RT. So, R and U is same in this case, x dot equal to Ax plus Bu. So, I am not writing the T in this case here. So, this will be my Y equal to Cx plus du. So, this is the open loop system description or block diagram of my plant. In optimal control, our objective here is we can have the feedback system in which either we are feeding back the state. So, if we are feeding back the state, so this will be my let us say K, and if I will take this negative, so my control law is U equal to, so I can write it journal, T is dropped in the figure, ut equal to RT minus KT XT. In most of the cases, if RT may be 0, which we call the regulator problem, discuss in detail later on, then my ut is simply minus KT XT. So, if I will apply the ut to my state equation, then x dot t will be At xt minus Bt Kt xt, or simply I can write as At minus Bt Kt xt, and this is nothing but my closed loop system. So, if my system is controllable, I can design a U in such a way, whatever be the condition of matrix A in this case, I can develop this closed loop matrix as I desired. So, I can get this matrix simply by getting the value of KT. So, this is called the optimal state feedback control. Similarly, as we are taking the feedback from the state, we can also take the feedback from the output Y. So, if I will take the feedback from the output, then this is called the output feedback system, and if I am taking the feedback from the state, then this is called the state feedback system. In this course particularly we will discuss state feedback system in detail and how to determine the optimal control law. So, I can say how I can get this optimal control law. So, what I can have? I can have a set point RT to be given, then this is simply my tracking control problem. If RT is 0, then the system is subjected to the disturbance, then this is simply my regulator problem. So, we will discuss in detail what is my regulator problem and what is my tracking problem. So, this is the way how we will model a plant. So, that is my first point. First of all, we have to get the mathematical description or model of the process to be controlled, and generally we have this modeling in state space form. To formulate a optimal control problem, once we will have the mathematical model, then we have to specify a performance index. Means what is our objective is to minimize or maximize a particular performance criteria. So, what is a performance index? We define a performance index as given here, let J equal to T0 to Tf x prime T Q x T. So, this is the minimization of the integral of the squared error. If we will take, then my performance index will be J. So, xt we are defining as xa minus xd, where xd is the desired value and xa is my actual value, or error can also be defined as xd minus xa. In any way we can define the error. This is basically the difference between the actual value and the desired value. So, our next point of discussion here is a specification of a performance index. Means we have to decide a performance criteria. Performance criteria is based on the what actually we want from our system. Like we will take, let we want to minimize the integral of the squared error in a given time. So, if my actual input is xa and the desired input is actual output is xa and the desired output is xd, then the error I can define as simply xa minus xd. So, if I will set my desired to be 0, like we said, take an example before, which is my set point. So, xd will be, in this case xd is nothing but my set point. So, if xd will be 0, then x nothing but will represent the actual state. So, in case of if r is 0, then this nothing but represent my state, but if I will take a set point, then this x nothing but represent my error. So, we are taking for a linear system, we are taking this as x prime qx. So, x in this case representing nothing but my error, q is the weighting matrix. So, x prime x giving me the square. So, this is square of the error, and the each state, like we have taken the n number of the states. So, in each state there are the n number of the error. So, for each error we are giving a weight which is defined by the Q matrix. So, my performance criteria is j equal to x prime qx, which is nothing but my integral of the square error. So, within a given time I want to extremize this, either minimize or maximize the value of the j. My next desire, maybe I will minimize my control efforts. So, control efforts means I will minimize my control energy. So, energy in any form I can represent as the square of my input, like I say the I square r. I square r is my power loss. I want to minimize the error to reduce this. So, any of the input square can be represented as the energy. So, ui square r may be any positive number, because if r is 0 or negative, then energy cannot be negative. So, and energy cannot be 0. So, r is a positive number. So, if there are the number of inputs, I can take j as sigma of ui square, means u1, u2, un, or in general I can write this, if u is a vector of say m cross 1, then u prime ru I can write as my performance criteria which I want to minimize, means I want to minimize the control efforts. So, in this r will be a positive definite matrix. So, ultimately my performance criteria will be u1 square r1 plus u2 square r2 plus u3 square r3 up to the number of inputs I have. And in each case, for the each input I want to the control efforts by the different inputs I want to minimize. So, I can write j as t0 to tf, means in a time period of tf minus t0. My objective is to minimize the control effort. This may be one of the choice, like the first choice was j equal to x prime qx. My next choice is the minimization of the control effort u prime ru. Another form it may take, let it j equal to x prime tf, f of tf, x of tf. This means I am trying to minimize the terminal cost. At tf is my final point. So, when I am reaching to the terminal, then I am trying to minimize the error, because x we have defined as the error. So, it means after completing of the interval t0 to tf, I am reaching to the tf, and after reaching, my objective is to minimize this terminal error. So, that will be my terminal cost I can define. So, j I can take as x prime f x of tf. So, in our optimal control problem, normally we will take a journal performance index which is defined as j equal to x prime tf, f of tf, x of tf plus t0 to tf x prime qx plus u prime ru. What this represent here means, in one performance index we are trying to minimize the terminal cost, we are trying to minimize the error, and we are trying to minimize the control effort. And this all we have discussed for a linear time system. The system which we have described, or the mathematical model we have seen, that was the linear time control system. As we have taken as the our A, B, C, D matrix are the function of time, this means I am considering the time varying system. Even here we are considering Q and R to be the function of time. So, this means this is a linear time varying system we have considered, for which we have seen the representation of my system model, and we have seen the performance index we can choose for such a system to minimize the performance index. So, complete formulation we will see in the next class. This class I stop it here. Thank you very much.